Hello Cloud Gurus, and welcome to this lesson where I'm going to provide an introduction into databases. So let's start with the basics. What is a relational database? At a very basic level, it's a collection of components. To start with, we have a physical or virtual server. As with most servers, it has processing capability, memory, and some locally attached or network storage. Installed on the server is an operating system, and this could be Windows, Linux, or something more of an enterprise grade. Installed onto that OS is a relational database system, and common well-known ones are Oracle, MySQL, and Microsoft SQL. These are the ones that you'll hear most about, but there are many, many more. Access to the database server is obtained via a client application, such as Microsoft SQL Management Studio, MySQL Client, or by utilizing an API or library, such as ODBC. And in some cases, this allows an abstraction away from the database being utilized, which is useful for application compatibility or porting. Lastly, and not to be confused with the name of the databases, you have access to the data using a specially designed language called Structured Query Language. And this is pronounced as SQL or SQL, depending on your preference. Queries can be executed against your database using the client application or within your application code. So let's start at a low level within our relational database management system. Relational database systems on the whole revolve around tables. A table is the most common base object within most databases and consists of columns and rows. Tables, if designed well, contain data which relates to other data in the table. It's well structured, and it's the same for every record in that table. And I'll spend a lot of time in the normalization lesson explaining what I mean by well-structured data. Rows are the records within a table. For whatever your database stores, everything has a row. Columns are the fields, and they store information for each record and define what that information looks like. Let's take a look at an example. An employee table for a large business. Nothing complex so far, but let's confirm the definitions I've introduced above. First, columns. And salary is an example of a column, as is employee ID, first name, surname, and all the other columns in the table you see on your screen. Next, we have rows, which represent a single record, in this case, an employee. And finally, we have a field, or in some cases, an attribute. The strict definition is where a row intersects a column, i.e. the department field in row 4. And to reiterate, in general conversation, the term attribute and field are often used interchangeably. A core concept of relational database systems is that the structure of the data in a table, the column names, restrictions on data, and keys are defined when you create the table, and this is called a schema. You couldn't, for example, decide that one employee should have his favourite pet recorded, unless you have defined that column for all rows in the table in advance. And in some database platforms, this can be adjusted afterwards, but there is a performance penalty. The next concept I want to introduce are keys. Keys are columns which have been designated special within a table. Their function depends on the type of key. Keys come in a few different types, the main ones being candidate keys, primary keys, and foreign keys. Candidate keys are any columns within a table that for a given value could uniquely identify a row. They can't have null or duplicate values. In our staff table below, examples of candidate keys are employee ID and national ID number. In some cases, tables will have existing columns which can function as a candidate key, but in some cases an auto-incrementing counter value, i.e. 1, 2, 3, or 4, or a uniquely generated value will have to be used as a substitute. The key thing to understand, pun intended, is that for a candidate key to be a candidate key, a single value of that key needs to be used to select one and only one row. i.e. if I provided a national ID number, it would match 0 or 1 row, not more than one, as the value in a given row for that column has to be unique. So next we have primary keys. And primary keys are just simply one of the candidate keys which have been selected to be keys for that table, i.e. to uniquely identify every row. In this case, options would be either employee ID or national ID number. If you don't have one single column which uniquely identifies every row, you can choose two columns to be a composite key, where both values together uniquely identify a row. And I'll talk more about this in the normalization lesson, but you generally use this when you have repeating data. The last type of key is a foreign key. And a foreign key maps to a primary key in another table. In this example, department is a foreign key, where the department code, for example HR or IT, would map to another table where the code is the primary key and is unique in that table. And in the department table for a given primary key, i.e. HR, the database may store additional information such as the department address, phone number, or the number of staff. The foreign key doesn't need to be unique in the table that it's in. So for example, we could have 2 HRs or 100 ITs in the employee table, but in the departmental table, there would need to be only 1 HR and 1 IT. It's worth mentioning that in relational databases, you have the concept of primary keys, and these may be called hash keys or partition keys in NoSQL databases. NoSQL databases don't have the concept of foreign keys as relational databases do, and as will become clear in this section of the course, that's because they lack the relational element of relational databases. But don't worry about this at this stage, we'll have a lot more information later in the course. Keys are critical to understand in order to be able to use relational database systems and SQL. And at this simplistic level, the concepts are the same for SQL and NoSQL databases. So let's introduce SQL, or Structured Query Language, at a basic level. SQL is a language used to interact with data in a relational database system, and it's formed of 3 main families of commands. We have DDL, or Data Definition Language, and this controls the database framework. It allows you to create, update, and delete tables, amongst other things. We also have DML, which is Data Manipulation Language, and this allows you to insert, delete, and update data within tables. And generally it also provides a command set to search data within the database platform. Lastly, we have DCL, which is Data Control Language, and this allows you to control a database so that conflicts don't occur. You can add restrictions and control valid data types, amongst other things. In practice, there isn't a distinction between the families in SQL. SQL is viewed as one language with a collection of commands. It's just useful to know the terms, as you may see them when working with database platforms. Now moving on, I want to talk about the structure of SQL, and this won't be extensive, just enough to get you used to reading SQL if you haven't had experience previously. So let's start with something simple, a query. A SQL statement is a collection of different command statements. The first is the select command, which is followed by star to indicate all, or the column names if you wish to retrieve specific column names. Next, we have from, followed by a table name, and this directs the SQL service at a particular table of interest. Next, we have where, which allows the database engine to select data based on the value in a column, i.e. select star from employee table, where employee ID is between 1 and 3. And lastly, we have order by, which allows one or more columns to be used to sort data. And the sort itself can be controlled with some extra flags. And there's also one other element, group by, which controls how the data is presented, but that's fairly situational. In my experience, it's not always used. Returning back to the employee table from earlier, I could run the following command to retrieve all the rows where department equals HR. Or I might do a range query on salary to pull all employees with a particular salary range. Or I might want to update somebody's salary, and that can be done with the update command. The syntax of this is slightly different, but follows roughly the same structure. Or if I wanted to outsource my IT and security departments and wanted to delete all rows in the employee table where people belong to those departments, I could issue a delete statement. And by now you should be starting to understand the basic syntax of SQL commands. So let's move on to talking about relationships between tables. And this is a key concept of relational database systems, the one that offers significant advantages over NoSQL platforms. I'm going to return to my trusty employee table again, but this time with some data pruning, and you will see why very shortly. I mentioned 2 slides ago that department was a foreign key, and I explained that meant it aligned into the primary key of another table. So let's look at what this means. You will see that the departmental table has 4 rows, each containing details of one department within the business. You can also see that those departments align with the 2 rows in the employees table. Because the departmental column in the employees table is a foreign key, there is a formal relationship between the employee and department tables, and I'll go into what this means and what it allows us to do shortly, but for now I want to call out the types of relationships that can exist between tables. Before I do, I'm stressing the term formal relationships. In relational databases, using a foreign and primary key establishes a link between tables that allows the database engine to perform complex queries. And officially, there are 3 types of relationships. One-to-one, and this is where each row in table A has a corresponding row in table B. Now in this case, this is clearly not true, as we could have multiple people in each employee table belonging to the same department. And next we have one-to-many relationships, and these are where one row in a table can match multiple rows in another table or vice versa. This is true in our case. Each row in table B, the department table, can match multiple rows in our employee table, as each department can have many employees. And finally we have many-to-many relationships, and this is where each row in table A can match many rows in table B, and that each row in table B can match many rows in table A. And this could be true in our case if a staff member was allowed to work in multiple departments at once. And this isn't the case right now, but in an upcoming slide I'll show you the architecture behind this and how we can make it work. By default, without modification to our tables, relational databases generally do not support many-to-many relationships, as it would need the department field in the employee table to store multiple values, and we will learn soon that this isn't allowed. So far I've provided an overview of simple SQL queries, and you've learned about table relationships. But what's special about these concepts isn't their use in isolation, it's how SQL can be used together with table relationships to perform complex query and manipulation operations. Let's have a look at an example. I present the employee table and the department table. What happens if we wanted to display the phone number, location and manager for all of our staff? How can this be accomplished with data in different tables? You could in theory handle this within your application, but unless you're a skilled developer, doing this at scale will take a significant amount of effort and processing overhead. What if the data you need is spread over 3 tables, or 30, or 300? What if each table has 1,000 or 1,000,000 rows? Relational databases and SQL is ideally suited to this type of operation, and it's highly optimized for just this situation. So you already know that you can select items from a table by running a SQL command, such as this one, to select all rows from the employee table, and this one to select all rows from the departmental table. What I haven't yet introduced is that the columns that we return can be filtered a little. For example, you can limit the query to retrieving just the column that you want. But as I mentioned above, I want to display the phone number, location and manager for all employees, and we can actually do that with SQL. The command is more complex, but let's step through it. The command selects the fields we want, but this time we're using 2 tables, so we need to specify the table and the column names in the select part of the statement. Then we specify both tables in the from section of the command, and we finish by having a where condition which matches the primary key of the department table and the foreign key of the employees table. And I want to spend some time describing how a table join works internally, so it makes more sense as to why that condition is there. So what's happening with the above SQL statement is that a join is taking place. Now, without that where condition, it would just join all rows from one table with all possible rows in the other table, and we'd have a Cartesian product. And you'll see why I pruned both tables now. So let's assume for a minute that the where clause wasn't there. What you would end up with is a conjoined table of results as below. Now, it's clear there shouldn't be 8 results. There should only be 2, one for each of the staff in our employee table. But because we're saying that the where condition doesn't apply, we get a product of each item in the first table with each item in the second table. And that's where we get our 8 rows. So what the where clause does is it matches the primary key from one table with the foreign key from another. And the results that are returned are only those where that result matches. And our actual result, based on that, is just the 2 rows that we want, where the department equals the department specified in the employee table. Let's stay with the same example and look at both of these tables. Each employee, so each row in the employees table, has one value in the department column. In this case, Joe has HR, Jane has IT, and we also have Bob in IT. Looking at this, it's clear that it's easy for a department to have more than one staff member, but to allow a many-to-many relationship, we would need to allow extra data in the department column within the employees table, i.e. by adding another department entry to Bob. And this isn't possible in relational database systems. Value in fields need to be atomic, especially keys, and we'll talk about this more in the data normalization section, so this won't work. The way we actually do this is via a bridging table. We create a new table which sits in the middle and restructures the relationship between the 2 tables into 2 one-to-many relationships. So let's see this in action. This table has a composite primary key of employee ID and department, meaning that only the combination of these 2 things makes each row unique, but it allows the database to model the many-to-many relationship. At the same time, the departmental column from the employee table would be removed. We'll talk about this concept more in the data normalization lesson which is coming up, as it's used extensively within retail applications where an order can have many items and an item can be stored on many orders. The key takeaway is that by using a bridging table and a composite key, you can create a many-to-many relationship via 2 one-to-many tables. And I expect this to make much more sense after the normalization lesson. I just wanted to introduce it here. Well, thanks for listening, Cloud Gurus, and that's the end of part 1 of the Database Fundamentals lesson. I would suggest you jump immediately into part 2, where we'll continue talking about the fundamentals of traditional database systems. If you have any questions, feel free to reach out directly or via the Cloud Guru forums. Otherwise, feel free to complete this lesson and move on to part 2.